This paper is joint work with Leora Fishman and Mario Sherbansky. Okay. All right, so I'll start with describing what's my theory of Diophantine approximation. What do I think it's about? Sometimes people will say it's about approximating irrational numbers or rational numbers, but I'll take the more general point of view that I want to consider a complete metric space, ZD, which will be analogous to the real numbers, a dense subset of which is analogous to the rational numbers, and some height function from my set of rational numbers to 0 infinity. And so then my question will be to try to approximate elements of Z by elements of Q with small height. Okay, so in this talk I'll talk about one example of things that you can put for Z and Q coming from dynamics. So I'll need the definition of a Gromov hyperbolic metric space. So I'll recall that here. Okay. See, I want to keep the projector on and the board, so I'll just not move the board up. So the Gromov product is this formula here. It's supposed to measure if we have a metric space in which all triangles look like this, the sides of the triangle are just unions of the GD6 connecting the points of the triangle to a common center, then the Gromov product exactly describes this distance from Z to the center of the triangle. And so, this is true. This metric condition is true if the metric space is a tree. More generally, any space that satisfies this condition is called an R tree. So they're sort of the prototypical examples of Gromov hyperbolic spaces. So a Gromov hyperbolic space will be one where the Gromov product acts as a metric. So somehow, in this picture, if this Gromov product is large, that should mean that X and Y look like they're close to each other from the perspective of somebody standing at the point Z. So, if it really is a notion of distance, then whenever 2 points are close to each other and one of the points is close to a third point, then the first point should also be close to the third point. And so that's precisely what this Gromov's inequality says. Okay, so I should say, what do I mean when I write this symbol? So A is less than sub plus B means greater than sub plus B means A is greater than or equal to B minus some constant. So so the constant is supposed to be independent of, in this case, the 4 points X, Y, Z, and W. In general, it should be clear from context what the constant depends on and what it's independent of. Okay. All right. So I'll give some examples of Gromov hyperbolic spaces. So the main motivating example is standard hyperbolic space. That's Gromov hyperbolic with the implied constant of log 2. Also, if we look at the complex and quaternionic analogs, those are also hyperbolic. We can even go to infinite dimensions. So that gives us an example of a non-proper Gromov hyperbolic space, one where closed balls are not compact. As mentioned earlier, trees and R trees. Almost every group is hyperbolic. This is a fact that was stated by Gromov and then proven rigorously by Olshansky. And then some more exotic examples, the curved graph of a finitely punctured surface and the Picard-Manin space, which I don't know what either of those things are, so don't ask me about them. So, okay. When we talk about Gromov hyperbolic spaces as being a generalization of standard hyperbolic space, this leads to the idea that there might be a generalization of the boundary. So So a big part of hyperbolic geometry is the existence of this ideal boundary. And there is a way to extend this to Gromov hyperbolic spaces. Basically, it works the same way as the definition of the completion of a metric space, except for a distance function, you use this e to the minus Gromov product. Okay, and then it turns out that when you try to extend functions like the Gromov product to the boundary, then they won't extend quite in a continuous way necessarily, but they'll sort of be almost continuous in the sense that continuity formulas will have an additive error term in them. Okay. All right. So then once I have this Gromov boundary, this is going to be my analog for the reals in Diophantine approximation. So now I want to put a metric on it so that I can tell how close is a rational approximant to the point it's trying to approximate. Well, this is a well-known construction called a visual metric, which says the distance between 2 points sine eta should be about e to the minus Gromov product of sine eta. Okay, well I don't want to put e to the minus Gromov product because that there are some hyperbolic metric spaces where e to the minus Gromov product doesn't give you a distance, but when you take a smaller power that's closer to 1, then it does work to give you a distance. Okay, but for a lot of the examples that we considered for all cat minus 1 spaces, then E actually works in this theorem. Okay. Okay, so let's sort of summarize what we have here. We have for the rest of the talk, I'm going to fix a hyperbolic metric space, and then this B, which is small enough so that I can always get a visual metric. And so then I have the reals, which are where I'll do Diophantine approximation. Now we want to try to get the rationals. So those are going to come from a group of isometries acting on my hyperbolic space, which will then extend to the boundary. So, okay, so I want my group to be discrete. Now, when I'm talking about a subgroup of isom Hn, isom Hn is a Lie group. It has a nice topology on it, so I can just ask for the group to be discrete as a subgroup of my Lie group, and that makes a nice definition. But in general, there is a topology you can put on the isometry group of a Gromov hyperbolic space, but the discrete subgroups of it are not very nice. They don't have all the properties we want, and so instead, I want to use this as my definition of discreteness, that if I fix any R and look at the set of isometries which displace some fixed base point distance of less than R, then that is always finite. Okay, and so that's geometrically somehow a nicer definition. Okay, and I also want to assume that my group is complicated enough that it doesn't fix any point of the boundary or the interior. So I'll say a group is a general type if it contains two isometries with north pole, south pole dynamics, and whose fixed point sets are disjoint. Okay, so there's a closely related notion of being non-elementary. A group is non-elementary if its limit set is uncountable, or equivalently if its limit set has at least 3 elements. But there are groups which are non-elementary but still aren't of general type because they have a single fixed point, but then also they have points in the limit set which aren't, which are not that fixed point. But I don't want to talk about those groups, so I'll just talk about groups of general type. Mm-hmm.
Do you require finiteness does it allow it to depend on the point? Or?
Yes, it is allowed to depend on the point. Yeah. Okay, so for the remainder of the talk, I'll also fix a strongly discrete group of general type. And so now I will let my rationals be the orbit of some distinguished point on the boundary under this group. And the height function will be the height of a point g of xi will be the distance from 0 to g of 0. I'll raise that to the power of b to make things work nicely with my metric. Okay, so the main example that we can think of throughout this talk is if my hyperbolic metric space is just two-dimensional hyperbolic geometry, and my group is SL2Z, and the point that I'm orbiting is infinity. Well, the orbit of infinity under SL2Z is the rational numbers, and it just turns out that this height function applied to this setup yields exactly, not exactly, asymptotically the square of the usual height function. So P over Q goes to Q squared. And if you interpret all the results that I'm about to say in this context, then they've been known for a long time. Patterson in 76 proved, I guess, most of them, and then the others were not too long after, I guess. But really, I'm mostly interested in having complete generality because that's nice. Okay, so I'll put a topology on the bordification of my hyperbolic metric space, by which I mean it's the metric space union the boundary. And I can define it in this manner. A sequence converges to a point in the interior if the distances tend to 0, but a sequence converges to a point in the boundary if the Gromov products tend to infinity. Okay. So having defined a topology, then I can define the limit set of the group that I'm considering, which is just the set of all accumulation points of some fixed base point. And so it turns out that this definition doesn't depend on base point. If I choose a different base point, I'll get the same set. Okay. All right, so now I want to look for finer structures within the limit set. So, okay, in regular hyperbolic geometry, then there's this notion of conical convergence, where a sequence is said to converge conically if there's some cone that you can draw, and so that the sequence of points that's approaching it is all within this cone. So I'll call that eta. But okay, I want to rewrite this definition in a way that doesn't depend so much on Euclidean geometry. So, all right, well, having them all lie within this cone, I could rewrite that as saying, well, if I draw a geodesic between my base point and eta, then all of these points are within a bounded hyperbolic distance of that geodesic. Okay, but I even want to do one further, I guess, rephrasing, because in the most general cases that I'm considering, the space is not necessarily geodesic. So even if my space is not geodesic, then I can say, well, this is equivalent to saying that the Gromov product of O and eta with respect to my points is bounded, which is the same as saying it's plus asymptotic to 0. And this is because of a condition of Rips that says if I'm in a hyperbolic metric space, then the distance from a point to a geodesic is plus asymptotic to the Gromov product of the two endpoints of the geodesic with respect to the point that I'm measuring the distance from the geodesic. Okay. All right, so that allows me to define the notion of radial convergence in an arbitrary hyperbolic metric space. I'll also define the notion of uniformly radial convergence to be where consecutive points have a bounded distance from each other. So with respect to my usual hyperbolic geometry, then that corresponds to when I draw sufficiently large uniform balls around all these points, then they entirely cover that geodesic. Okay. And so now I can define the radial and uniformly radial limit sets as subsets of a limit set, which occur when I demand that there's a sequence of points in the orbit of my base point which converge.
The two definition of radially and uniformly?
Yeah. Okay, so these definitions give me subsets of my limit set. I'll just mention in the special case where the group is SL2Z, then the radial limit set turns out to be the irrational numbers, and the uniformly radial limit set turns out to be the set of badly approximable numbers. Okay. Next I want to talk about the Hausdorff dimension of the radial and uniformly radial limit sets. So there's a formula for this, which was proven by Bishop and Jones for the standard setting, but then was generalized by the paper that by my joint work with Fishman and Urbanski. So the formula depends on the Poincare series, which is this series sum over all group elements of b to the minus s times distance from 0 to g of 0. The Poincare exponent is the exponent of convergence of the Poincare series. That's either the smallest value where it converges or the largest value where it diverges. Okay, so then...
So I'm wondering,
yeah.
when X is locally compact and G is compactly generated, is the same uniformly radial and radial, or it's not the same?
Sorry, wait, say that again. X is locally compact.
And G is compactly generated or finitely generated.
And G is finitely generated.
Is it the same to be uniformly radial? And
it
is the
should...
uniformly radial limit set the same as the radial?
Okay, so wait.
Okay, it's okay.
I think
asking whether it was this.
Okay, I think so. So okay, so in the case, let me say this, so that if the orbit of a base point is co-bounded, then the uniformly radial limit set is equal to the entire boundary. Okay. Yeah.
So sorry, can you say again in the SL2Z example? So uniformly radial. Can you say one is bounded badly approximable?
Yeah. Yeah. So the radial limit set is irrationals, and uniformly radial is badly approximable.
Yes.
Yeah. Okay. Okay. Yeah. So as I said a minute ago, the standard finite dimensional hyperbolic geometry case was proven by Bishop and Jones. Paulin at the same time proved a number of partial generalizations. He considered Hadamard manifolds, uniform trees, and word hyperbolic groups, but he still didn't state the general case. Okay. All right. So that finishes the introduction to my talk. So now I'll start stating the main theorems, which have to do with Diophantine approximation. All right, so I consider the main four theorems of Diophantine approximation to be Dirichlet's theorem, the Jarnik-Schmidt theorem on the existence of badly approximable numbers, Khinchin's theorem, and the Jarnik-Besekovich theorem. So I'll go through each of those four theorems and say what's the original theorem, what's the generalization. So first is Dirichlet's theorem. So the generalization will say that for any point eta in the radial limit set, then I can find a sequence of points in my analog of the rational numbers whose distance to eta is less than a constant times 1 over the height, so b to the minus distance from 0 to g of 0. Okay, and so if we compare this with the classical theorem, then they're pretty close. The only difference that we really see is in here we have 1 over the height, and here we have c over the height. We've added in a multiplicative constant, but this is not really too unreasonable based on the kind of things that we're considering. We had to add in additive asymptotics in a lot of different places here, and whenever we convert that into, so here we've obviously taken an exponent, so that should convert additive asymptotics to multiplicative asymptotics. So somehow this is just a consequence of we're really interested in more coarse geometry concepts rather than finer distinctions.
Did you say the distance is 1 over the height or height squared?
Right. So okay, that was the other point I was going to make. So it looks like here it's 1 over height squared, but if we go back to this slide, then we remember the height that comes from looking at it as an orbit is actually the square of the denominator. So I always want to think of denominator squared as really being the height in this talk, because that'll sort of make things line up more. Okay. Yeah. Right. Yeah. That is a little counterintuitive sometimes, though. Okay. All right. So we've proven the analog of Dirichlet's theorem. It actually turns out not to be too difficult to prove that based on the definition of the radial limit set. But the Dirichlet's theorem shouldn't really be considered significant until you can show that it's optimal, meaning that you can show that it can't be replaced by any Dirichlet's theorem which says that we can get a sequence of points converging faster to the point. So how can you show such a thing, that there's no theorem better than Dirichlet's theorem? Well, you can show that there's badly approximable points, which are points such that when I multiply by epsilon, then the reverse inequality of Dirichlet's theorem holds. Okay, so that's the definition of a badly approximable point. And so if we can show that there exists a badly approximable point, that demonstrates that Dirichlet's theorem is optimal. Okay, and so then, in fact, we can prove not only the existence of badly approximable points, but actually their full dimension within the radial limit set. Okay, so classically this was proven by Jarnik, and then generalized to higher dimensions by Schmidt. Okay. The existence of badly approximable was proven earlier, but the full Hausdorff dimension was proven by Jarnik. Okay. All right, so I want to give an idea of the proof of this theorem. So I mentioned the Bishop-Jones theorem earlier. The reason I mentioned that is because the proof of Bishop-Jones theorem actually has a lot in common with the proof of this full dimension of badly approximable theorem. Basically, the proof of the badly approximable theorem will just be the proof of the Bishop-Jones theorem with some additional work. Okay, so let's let delta be the Poincare exponent. Okay, here I've written hd of lambda r, but really that will only be clear after the fact that it's equal to lambda hd of lambda r. And so then, given any s strictly less than that, then we'll construct a subset of the uniformly radial limit set, which is the topological support of an Elford's regular measure, and also has a sort of symbolic structure. There's a coding map from some subset of there's a coding map from some tree to the set JS. Okay. And so then once we've constructed this set, then it has large Hausdorff dimension because it's alpha is regular with that dimension. But now we want to also show that its intersection with BA also has large dimension, and so this is where Schmidt's game comes in. So actually we don't use Schmidt's game. We use a variant of McMullen, which is called absolute winning. Okay, so I'll describe that game. So suppose we have a complete metric space K. Ellis and Bob play absolute winning game by Bob chooses a ball. Then Ellis chooses a subball of that ball with a significantly smaller diameter. You should think of beta as being fairly small. And we think of her as deleting that ball. So from now on, after Ellis plays that ball, Bob has to choose another ball outside. So if we want to draw a picture, here's Bob's ball B0, Alice deletes this A0, and then Bob can move anywhere else. And then, okay, then she deletes another set, Bob moves them there, and then you can take the limit. And because we're in a complete metric space, then we're going to get an intersection point.
I think you don't want to force A0 to be a subset of B0. You're just restricting.
Yeah, you might be right.
But yeah.
Yeah. Okay. Yeah. Okay. Yeah. That might be right. Yeah. Okay. Yeah. Okay. So okay. So since it's a complete metric space, then this process will have a unique intersection point. We'll call that the result of the game. And so now a set is said to be winning if Alice can always force the result of the game to land in that set, regardless of what regardless of how small the parameter beta is. So it should be clear that the smaller beta is, the harder it is for Alice to win. Okay, and so then what we'll actually prove is that BA is absolute winning on this set JS that we constructed. And so then there's a theorem of Fishman that says if we have a topological support of an alpha's regular measure, then an absolute winning, or actually even just a winning set, even though I haven't defined what that is always going to have full Hausdorff dimension. And so then this means we can intersect with each of these sets JS, we get full dimension there, and then taking the limit as delta approaches s approaches delta gives us full dimension. Okay. All right. So what else do I want to say here?
What do you call the topological support?
What?
What do you call the topological support? What's the definition of topological support?
What's the definition of topological support? I mean,
It's
it's just the smallest closed set that has full measure. Yeah. Okay. All right. Okay. So next, I'll move on to the Yarnik-Besikovich theorem. So this theorem is about exponents of irrationality of numbers. So the exponent of irrationality of a number. Do I have that written? No, I don't. Okay. So basically, if I consider this inequality, x minus p over q is less than q to the minus tau, for every tau, this will either be satisfied infinitely often, or it won't be satisfied infinitely often, or it will be satisfied only finitely often. And so the larger tau is, then the harder it will be to be satisfied. And so then the point where it crosses from being satisfied to not being satisfied is called the exponent irrationality. And so then it's fairly easy to take that condition and rewrite it as a lim sup, as I've done in the slides here. And okay, so here I guess I've done the confusing thing of putting q up here and the regular height over there. I should have put in q squared here. But the difference that will end up causing is that this number is going to be the double of this number. Okay. All right, so now we can define the Yarnik sets to be super level sets of the exponent of irrationality. So equivalently, these are sets where this inequality will be satisfied infinitely often. Well, okay, well that's not the exact name, but the difference won't be important in terms of Hausdorff dimension. Okay. All right, so the Yarnik-Besikovich theorem asks this question: what's the Hausdorff dimension of these Yarnik sets? Okay, and we can also ask about the sets VWA of sets whose exponent of irrationality is strictly greater than the minimum, which is 1, and the Liouville numbers is the set of points whose irrationality exponent is the maximum possible, which is infinity.
What's the dependence zeta?
Yeah, it depends on psi because these are the dynamical versions of VWA and Liouville. So
Can you just the previous slide? Where's
yeah, so right, so I'm looking at the in the top thing I'm looking at the orbit of psi, and that's the analog of the rationals, and so that's why it depends on psi.
Psi tells you who the rationals.
Yeah, psi tells you who the rationals are. Okay. Okay, so in the classical case, the answer to all these three questions are very simple. The Hausdorff dimension of Jarnik sets is given by a rational function, 1 over 1 plus c. And then this shows that the VWA have full dimension and the Liouville numbers have 0 dimension. Okay, so in the general case, then it's going to be a bit more complicated than that. It'll depend on the geometry. So to describe exactly how it depends on the geometry, then I'll talk about the Hausdorff content, which we remember is an intermediate step of defining Hausdorff measure. And then I will look at, so basically I have this point psi, and I want to know how big is the limit set near psi. And so, okay, I can look at a ball around psi and intersect it with the limit set, and then measure the Hausdorff content of that intersection. All right, so that's this number here. And as r varies, then that tends to vary as a power of r. Okay, which power of r is it varying as? That we can answer by demanding that peak psi of s should be the largest number such that this asymptotic formula holds. And then again, we can rewrite that as a lim-int condition, like this. Okay. So you may notice that there's a lambda r sigma here going on, and then I'm taking the limit as sigma goes to infinity. This is really a technical condition which should be able to be circumvented in a lot of circumstances because so LR sigma is the set of all radial limit points that such that the uniform bound on the distance to the geodesic is less than sigma, or I guess I should say the Gromov product condition that I said that should be less than sigma. Okay, but really, if I eliminated the limit and just put intersection with lambda r, I would get the same thing in most circumstances, but I can't prove that it would happen in all circumstances.
In the definition of Hausdorff content, do you require it to be an epsilon cover? Or
for Hausdorff content, then I want to look at all covers, not just epsilon covers. So that's what makes Hausdorff content different from Hausdorff measure. Yeah, that I'm allowing all covers. Yeah. Okay, and so now I can state my generalization of the Jarnik-Besekovich theorem. It ends up looking a bit like Bowen's formula. So I have this function p psi, which may look something like this. And then I want to intersect it with the curve delta minus s over c as a function of s. So this is the x-axis. This is, okay, well, I won't label this axis. So this is peak psi of s. This is delta minus s over c. And then the Hausdorff dimension of WC psi is going to be, I take the point where they intersect, and then the s coordinate of that point is the Hausdorff dimension. All right, so I haven't stated that the Hausdorff dimension is the unique zero of this difference because we may have a picture like this, where there's a gap here, but then the delta minus s over phi passes that gap. But in that case, I would want to consider this number to be the Hausdorff dimension, and so that I can get by defining it with this sup and int definition. Whereas stating that it was the 0 would be a bit more specific, and that's not true in general.
What's an example?
It's kind of hard to say what the examples are exactly, but you can sort of like play with things a lot. There's something called infinitely generated Schottky groups are a good source of counterexamples for these kinds of things. Yeah. So a nice thing about this Hausdorff dimension is there's always an upper bound for it, which is delta over c plus 1, which is actually the bound that turns out to actually be achieved in the case of SL2Z. I guess it wasn't on the previous page, but all right. So what does this say about VWA and Liouville? Well, the Liouville numbers will actually get that those have Hausdorff dimension 0 because the upper bound is good enough to guarantee that. As c goes to infinity, then that expression will approach 0. But the VWA are a bit different because we could have a picture like this, where, okay, this is representing infinity. The peak psi starts going up, but then it eventually just goes all the way up to infinity. And then, regardless of what c is, you'll always have Hausdorff dimension at the same level, which is less than delta. And so then the Hausdorff dimension of VWA could be strictly less than delta. Okay. All right, and I think we have an example of the paper in the paper of where VWA does have Hausdorff dimension strictly less than delta. Okay. All right, so I'll say a little more about this geometric interpretation of the peak psi formula. So basically, it says the more dense that my limit set is around psi, then the larger this left-hand number will be. Well, the larger that number is, then the smaller exponent I need in order to make this formula work. So the smaller peak psi will be. But then the smaller peak psi will be, that corresponds to moving this graph down, or moving this graph, yeah, down. And so then that would increase the Hausdorff dimension. And so the limit, if the limit set is dense near psi, that corresponds to Hausdorff dimension of WC psi being large. Okay, which, if we interpret it informally, that means if I can approximate a point very well by points of the limit set, sort of in some measure theoretic sense, then I can also use that point psi that I'm approximating. That's very good at approximating other points. So this is a nice intuitive interpretation, I think, because I mean, it's a group. If I can move something from one point to close to psi using an element of G, then by using the inverse of that element, I should be able to move psi back to the original point. So obviously the rigorous argument is a lot more complicated than that, but that's sort of the fundamental picture, I think. Okay. All right, so let's talk about some special cases. So what if psi is a radial limit point? Well then, if you look at the formula for peak psi, then it actually ends up equaling, being identically equal to s. The reason for this is because if I have a radial limit point, then infinitely many times I have this point in the orbit of 0 that is close to the geodesic. Now, if I move the entire limit set forward by this guy, then there's a significant portion of the limit set which ends up moving in this ball that this guy sees. And that significant portion is enough to give a lower bound on lower bound on the Hausdorff content, and then that translates into this peak psi s equals s, which is the lowest possible, and that corresponds to the Hausdorff dimension being the highest possible, which is delta over c plus 1. Okay, well this also makes intuitive sense because radial limit points are the most possible to approximate because their sequence of approximations is lying boundedly close to a geodesic. In an asymptotic sense, that's almost as good as having them lie on the geodesic, which obviously you can't get any faster than that. So that makes sense. Okay, so I'll also talk about parabolic limit points. So okay, so in the standard hyperbolic geometry, there's this notion of a bounded parabolic point, which is defined by saying that when I look at the limit set minus this parabolic point, and modulo that by the stabilizer of the parabolic point, then I should get a compact set. Okay, so this definition, I claim, should translate into this definition in the more general case. So let me draw a picture. Eraser, where's eraser? This is an eraser. Okay. Okay. All right, so here's my point psi, and to say that my parabolic point, the first two conditions just say that my point is parabolic, but my third point is supposed to be saying that my point is a bounded parabolic point. Well, I want a set S, whose closure does not contain psi. So here's what such a set S would look like, and then I want the orbit of that set.
What is G prime in the second condition?
Oh yeah, right. Sorry. So G prime. Here I'm taking a metric derivative. So that is the limit as eta approaches psi of d g eta g psi over d eta psi. All right. So this limit will exist in an asymptotic sense. The lim sup will be times asymptotic to the lim inf, and so I could use either of these numbers as the derivative without losing too much. Okay. And so then I take this set S and translate it by p psi. So I get these points here, and so then I want to say that my set is my point is a bounded parabolic point if this orbit contains the entire orbit of 0. Yeah. All right. So it takes some work, but you can show that this condition is equivalent to the usual one in the standard case. Okay. All right. So now that I've defined a bounded parabolic point, I can state what does my peak psi function look like if psi is a bounded parabolic point? Well, it will equal the maximum of S and 2S minus 2 delta, where delta is the Poincare exponent of G. Okay, so that gives us a piecewise rational function. HD of W seek psi is a piecewise rational function of C. All right, and so this was already known in the standard case, so it was proven by Villani and Hill. And in that case, we can write the Poincare exponent of a parabolic group is equal to 1/2 of the rank of that group. So that means really they wrote their formula in terms of the rank of the parabolic point rather than the Poincare exponent. So this generalization from going to the rank of a parabolic group to a Poincare exponent, it sort of sounds like it might be trivial, but actually it's pretty complicated because parabolic groups in an arbitrary Gromov hyperbolic space can look very crazy. So if I look at the function R goes to cardinality of G such that the distance from 0 to G of 0 is less than R, then if I'm in Hn, then so let me call this function n. So then n of R. Actually, I want to use the capital D. So then in Hn, n of R will be asymptotic to R to the k for some k. But in general, then I can get n of R is asymptotic f of R for any f, for any increasing f. For any increasing and doubling f. By doubling that, I mean that if you take f of 2R, then that will be times asymptotic to f of R. Okay. So based on this this theorem here, we can see that these are both for parabolic. we can see that parabolic groups in general Gromov hyperbolic spaces can be a lot more complicated than ones in usual spaces. So actually, when we were trying to come up with this example, we thought that the Hausdorff dimension might end up depending on not just the Poincare exponent, but sort of more detailed information about this orbital counting function. So it was sort of surprising that it ended up only depending on this single number of the Poincare exponent. Okay. All right. Okay, so I guess I don't have that much time to go through Khinchin's theorem, but I'll see what I can say. So in the theorems that I've talked about so far, we've talked about either a statement that happens everywhere, Dirichlet's theorem, or a statement about Hausdorff dimension. The Jarnik-Schmidt theorem says that the badly approximable have large dimension, and then the Jarzik-Bezikovich theorem calculates the dimension of well-approximable sets. So now I want to change and go to the measure theoretic category. Well, in order to do that, then I need a nice measure acting on my Gromov hyperbolic space, which I haven't said what the measure is. I'm going to skip over to the next slide to say what the measure is. So the measure that I want to put is going to be a quasi-conformal measure, which is a measure that satisfies this asymptotic formula here. So Patterson and Sullivan proved in the standard case the existence of measures which satisfy this formula with equality. Of course, in general, we won't be able to expect equality just because of this coarse geometry thing. So asymptotic is the best we can hope for. Okay, so there's some theorems saying that we have existence. Cornier proved that if we're in a proper hyperbolic metric space, closed balls are compact, then there does exist a quasi-conformal measure. And Grishoning and Schmidt have an ergodic decomposition theorem that applies to this setting and means that you can decompose any quasi-conformal measure into the integral of ergodic quasi-conformal measures. Okay, so that's the measure. So let's also talk about what sets do we want to measure. These will be sets of well-approximable numbers. So if I fix any function phi, then I can look at the set of all eta such that eta can be well approximated by points whose distance to eta is less than phi of the height. And then I've added in a constant factor for coarse geometry reasons. Okay, so I'll fix a quasi-conformal measure mu and approximation function phi. All right, so since mu is ergodic, then the measure of well-approximable will either be 0 or 1. And so the goal of Khinchin's theorem is to figure out which it is. All right, so to make these statements more compact, I'll define the ball measuring function delta of r is equal to mu of b psi r, where psi is the point that I'm approximating by. All right, so here's our generalization of Khinchin's theorem. So in general, Khinchin's theorem should depend on some series. So if this series diverges, then well-approximable are full. And we have a different series that if it converges, then the well-approximable are 0. And if we're in the case of a bounded parabolic point, then these series, then we can get the series to be the same, because if the divergent series converges, then we can get measure 0. But that's only for bounded parabolic points. So okay, so maybe I should have been making more of a point of this earlier. So all the results previous to us, there was like about 10 or 20 papers concerning related topics, but they all sort of had a more narrow focus on basically the standard case, and G is geometrically finite, and psi is a parabolic point of G. And so the big thing is, in our paper, we removed all these assumptions. But here we can remove the assumption of G being geometrically finite, but we can't really remove the assumption of psi being a bounded parabolic point if we want an equality. Actually, that's not entirely true. So some of the theorems I'll show on the next slide will give an alternate way of getting equality. But in general, it looks like we're not going to be able to get rid of the gap because, okay, so basically, why can we close the gap if we're considering a bounded parabolic point? Well, if you're considering a bounded parabolic point, then there's it has a large stabilizer, right? And so that means the orbit map is highly non-injective. So somehow when you're measuring all these balls, then you can when you're considering balls around some point, you can really just consider the first instance of a ball around that point and then ignore the measure of all the others. But in general, we could be in some situation where this map is not injective, and so then these balls are really just going to be a bunch of balls in different places, and so then why should there be cancellation? It's not clear. And so yeah, so we know that the convergence series is not the correct series. We think the divergence one is correct, but we can't show that if that series converges, then we get the right answer. Okay, so now I'll talk about some situations under which you can simplify the series, because obviously they look pretty horrible, right? So there's two assumptions which are useful. The first is a power law on the orbital counting function. We want the number elements where d of 0, g of 0 is less than t to be asymptotic to b to the delta t. And second is a power law on the ball, which is this delta mu psi of r is asymptotic to r to the delta. Which I only need the power law for a neighborhood of psi, not for every point. So that should be pointed out. Okay, so these are both satisfied for SL2Z. I guess I should also mention, if either of these is satisfied for any exponent, then they have to be satisfied with the exponent delta. It's impossible for them to be satisfied with some exponent other than delta. Okay. So if my power law asymptotic for orbital counting functions holds, then I can reduce the divergence series to just a single integral that depends only on, I guess, the ball counting function. Okay, so I think the most interesting one are the second and the third. So the second one says, if I have a power law on the ball measuring level, then the divergence and convergence series are asymptotic. So there the gap goes away. And if I have both of the asymptotics, then I can actually reduce everything into a single integral. So just the integral of e to the delta t, phi to the delta of e to the t dt. And so there it doesn't depend on anything about the group other than that it satisfies these two power law asymptotics. Okay. All right, so I think I'll stop there then.
Okay, any questions?
Mm-hmm.
Yeah. Can you? I guess you could define an analog of the cuspidal limit set.
What's the cuspidal limit set?
So you don't stay in a cone, you stay outside of any cone. That you can be approached by a sequence of points.
So wait, you want a sequence of points approaching eta that no subsequence of them is a radially approaching sequence.
Yeah.
I see. Huh, that's interesting. Okay.
There are, like in the classical cases,
Mhm.
there are statements about the Hausdorff dimension being something like the exponent or something.
Half of the Poincare exponent.
Yeah.
Okay.
So.
Huh.
Yeah.
That's interesting. Okay.
This is all, you mentioned the analogs of the classical
Mhm.
Diophantine approximation. There are sort of extensions to linear forms and stuff like that. Is this possible?
Yeah. So here's what I want to say about that. Basically, we don't expect to be able to extend these to refer to any Diophantine approximation phenomenon which is not essentially rank 1 in some way. So Diophantine approximation in higher dimensions is usually considered to be a higher rank phenomenon, whereas hyperbolic spaces are considered to be rank 1. On the other hand, we do have some examples of rank 1 Diophantine approximation, which is rank 1 and so can be approximated by these hyperbolic. So one of those is approximation by the in complex numbers by fractions of Gaussian integers, or approximation in p-adics for single p-adic numbers.
What about things like
Quaternionics, yeah, you can do it for quaternions as well. Yeah. Mm-hmm. Yeah. Yeah, and then there's also intrinsic approximation on quadratic varieties, which also turns out to be rank 1 if the quadratic form is rank 1. Mm-hmm.
I guess this is kind of a joint question for you and Corina, when she mentioned infinitely generated Schottky groups.
Mm-hmm.
So I was wondering if it would be interesting to try and do Diophantine approximation on so you take a flat surface whose Veitch group is infinitely generated. We have examples of these things.
Go ahead.
And try and do what Corina did yesterday in terms of approximation on the boundary at infinity. See what I'm saying? Right? Yeah. Interpret it in terms of the flat surface. I guess it's more a suggestion that you talk to each other.
I see.
Do you have example where the series div and conv are not multiplicatively equivalent?
Yeah, sure. So okay, so I guess I didn't explain this comment in detail. We have examples of ones where the convergence series diverges, but still the measure is 0. And so in those cases, obviously the divergence series converges, the divergence series diverges, but then the measure is 0. Those are what we have examples of. Yeah.
Okay, so we'll send the Okay, so I guess there is another talk by Eve. It would be
Informal talk.
informal.